Hello, friends. Welcome to another session on 8051 microcontroller programming. In this session, we are going to discuss about instruction set. So we will classify the instructions logically, and we will discuss each set of instructions in detail. So let's begin. So instructions are classified into five different categories. Data transfer instructions, which helps in transferring the data, as the name itself says. All the classifications are self-explanatory actually. Arithmetic instructions perform the arithmetic operations. Logical instructions perform logical operations, that and or XOR not, like that. And boolean instructions we have for set, reset, not operations. Then we have call and jump instructions. Call is for the function calls or subroutine calls. Jump is both conditional and unconditional jumps. We'll see the instructions in each of these classifications one by one. First, coming to our data transfer instructions, these instructions are used to transfer the data from one location to another location. When I say location, it can be a register or a memory location. So, first couple of instructions we are quite familiar with. That is, first one is move a comma a r register. R it is given. That means we can use any register there. R0 to R7. So the data from R register is transferred to accumulator. It is copied, basically transferred in the sense the R also retains the original data and the same data is copied to accumulator A. Then next, move a comma address. This is a direct addressing mode, wherein instead of register name we are giving a directly a address of a memory location. From that the data will be read and copied to accumulator. Then move a comma at rp. This is a register pointer. Only r0 and r1 can be used here, which will contain the address of a memory location, and data will be read from that location and moved to a. Remember, rp is a 8-bit register, so it is usually used with the data memory only, but we can use that with the external memory also if the size is within 8 bits. Address size is within 8 bits. Then move rr comma hash data. This is immediate addressing mode instruction, wherein the required data is directly available in the instruction itself. Then we have move dptr comma data hash data. So dptr is a data pointer, which is a 16-bit register. However, this dptr can be used as a 2 8-bit register also, that is data pointer higher byte and data pointer lower byte, dph and dpl. Then we have a move x instruction. So this instruction is used for the external memory access. As I already told, we have a separate instruction for data memory, code memory, and external memory. So only move instruction is used for the data memory access. Move x is used for the external memory access, and move c is for the code memory access. Now move x at rp comma a, where rp is again a register pointer. As I said, in this case, the size of the external memory should be less than 256 bytes. That means we can address only 256 bytes of memory location because rp is a 8-bit register. If we want the higher memory addresses, then we have to go for data pointer, that is movex comma at dptr. This will access entire 64 kb of the memory because dptr is a 16-bit. Then move c a comma at a plus dptr. This we have already discussed. This is the indexed addressing mode, where a will carry the base address and dptr will have the offset. Instead of dptr, we can also have a program counter there in some cases. Then that particular memory location is read and copied to accumulator. Then we have one more instruction, xch. This is exchange instruction. So the content of a and rr, that is register, is exchanged. These are data transfer instructions. The next set of instruction is arithmetic instructions. In arithmetic instruction, we have a add command. So that will add the two registers as we already seen in the previous session. The content of register is added to A and result is stored in A. Then we have a add C, that is add with carry flag. Now the content of RR is added to accumulator, and also carry is also added, and the result is finally stored in A, and also carry flag is updated with the newer value. Similarly, we have subtraction with borrow. We don't have only sub, it's only subtraction with borrow. The same carry flag is used as a borrow here. The same flag will be used. That is A minus RR. That is the register content is subtracted from the accumulator and result is stored in accumulator after subtracting both content of register and carry flag. Then you have multiplication MULAB. This can be used only with the AB. We cannot use any other registers here. So when we multiply the content of A and B, the result might be more than 8 bits. So lower byte of the result will be in the accumulator and higher byte of the result will be stored in B register. Similarly, when we perform a division operation, this is also done with only AB, A by B. So after division, A will contain the quotient of the division, B will contain the remainder. Then one more instruction we have is decimal adjust DA instruction. So this is performed whenever we are doing BCD operations. The whatever the result we get, if we want to adjust that result to a BCD value, then the decimal adjust is used. Then we have increment A and decrement A. So these are increment and decrement instructions to increase and the value by 1 and decrease the value by 1. Then we have next set logical instructions. First one is ANL, that is AND logic. So the content of A and register is ANDed. Here we can give a immediate data also for the AND operation. So again, the result will be stored in accumulator. Similarly, we have OR logic and XOR logic. Here also the content of A is ORed with register content or immediate data, and result will be stored in accumulator. And in this case, in the XRL, the content of R is XORed with the content of accumulator or immediate data, and then the result will be stored in accumulator. These are the three logical operations. Then we have clear A, that is to clear the content of accumulator. And we have one more instruction, that is swap. Remember, swap is different than the exchange command. Swap will have only one operand. So we will have a lower nibble and higher nibble exchanged, not the bytes. It's a nibble exchange of the same register, that is accumulator. It can be used only with the accumulator. Then we have a NOP, that is no operation. The next set we have is a Boolean instruction. In Boolean instruction, we have again bitwise AND logic here. That's a Boolean operation. So you can see the operands are bitwise operand. We already have discussed that. The microcontroller understand or identify the instruction, whether it's a bit or a byte, based on the operands or instruction. In these first four cases, it is identifying the instruction as a bitwise operation based on the operand, whereas in the next two are anyway a bitwise instructions only. So here AND logic carry flag with a bit given. We can give whatever the bit we give, that bit will be ANDed with the status of the carry flag. Similarly, we have OR logic. So whatever the bit is mentioned, that bit is ORed with the carry flag. Then this is a complement of the carry. So if the carry is 1, then it will become 0. If it is 0, it will become 1. Similarly, we have a bit. We can give any bit for the complement of that also. That will also get complemented. Similarly, we have data transfer, that is bitwise. So bit of a data can be transferred to carry flag. I'm giving example with the carry flag. This can be used with all the other bitwise registers. That means whichever bitwise register we have, we can access all those bits in using these instructions and perform these operations on them, whether it's a port bits or it is a SFR bit or a PSW bits or accumulator bits. In all the registers, we can use that. Then we have a set bit C. This will set the status of the particular bit as logic high, and clear C will set the status of the particular bit as logic low. These are Boolean instructions. Then finally, we have a call and jump instruction. In this we can see first one is djnz rr comma r address, that is a relative address. So this is relative addressing mode. Decrement and jump if not 0. So what it will do, it will decrement the content of R register, and then it will check if the register value is 0. If it is not 0, then it will jump to the address given. I repeat, this instruction will first decrement the content of register R, then it will compare the value of the R with the 0 after decrementing. If it is not 0, then it will jump to the label. So this will be used in the loop operations. This is a conditional looping. Then we have a sjump, that is a short jump, sjmp, and we'll give just a address. Address is given in terms of label, not the direct address. It can be given just as a labels also. Then sjmp is an unconditional jump. So there is no condition checked. Whatever the label we give, direct it will jump there. Then we have CJNE, that is compare and jump if not equal. Here we have three operands, RR, hash data, and address. So the content of register and the data given are compared. If they are not equal, then it will go to the label mentioned. If they are equal, it will continue the sequential operation. Otherwise, it will jump to a label mentioned. Compare and jump if not equal. Then we have a call instruction, that is the absolute call. So this call operation happens within the particular page or a segment. Then we have some more conditional jumps like JC, JNC, that is jump if carry flag is set, jump if carry flag is not set, or carry flag is cleared. Jump if carry, jump if no carry. Again, we will be giving the labels here for where to jump the control. Similarly, we have jump on bit and jump on no bit. Here we have to give which bit to be checked. Whereas in this case, we know that carry is default, it will be in the PSW only. So we don't have to worry about that. The controller will directly go to that particular bit and it will check the current status of that. Whereas if we say JB and JNB, that is jump if bit or jump if no bit. In that case, we have to mention which bit has to be checked by the controller. So we have to give the bit value or the bit address and the label. Then finally, we have two instructions, that is return and return from interrupt. So return is used whenever we call the program using a call, and then we are coming back from the subroutine using a RET instruction. Whereas RETI is used whenever the control moves to an ISR, interrupt service routine. While coming back, we will be giving a RETI as a last instruction in the ISR to come back to the main function. So this RETI again I will be explaining when we are discussing with the interrupts. Okay. So that's it for the video. Thank you. Have a good day.